So last night we had a little bit of homework, worksheet number 25, all based on this half-life calculation stuff that we did yesterday. Essentially, the idea of half-life comes down to the definition of half-life and a couple equations. We defined half-life as the time that it takes for half of a radioactive sample to decay. So let's say we start off with 10 kilograms of a radioactive sample, and the half-life of that sample is 2 years. And after 2 years, you'll be down to 5 kilograms of that radioactive sample. After 4 years, you'd be down to 2.5 kilograms of that radioactive sample. Statistically, half of it will decay in one half-life, whatever the half-life is. Different for every element, right? Okay, for one element, it might be 2 years. For another one, it might be 5,000 years. For another one, it might be 3 seconds. Okay, but half-life, the time that it takes half of it to decay. Now, when that 10 kilograms decays into 5 kilograms, it doesn't mean the other 5 kilograms is just gone. It's just vanished. It isn't. It's still there. You still have 10 kilograms. It's just that 5 kilograms has decayed into something else. So you got 5 kilograms left of what you started with, and then 5 kilograms of something else. It's transmutated into something else. Now, in order to analyze this mathematically, we look at two equations. The first one being an equation that you could have figured out on your own. And that's good because it's not on your data sheet. We say the number of half-lives is equal to the total time divided by the half-life. This goes back to Unit 2, our electricity unit. I asked you in Unit 2, how many electrons do we have, blah, blah, blah. How'd you find that? Well, you took the total charge and divided it by the charge of one electron. The total charge by the charge of one electron. Okay, in our EMR unit, I asked you for the number of photons. And you calculated that by saying it's the total energy divided by the energy of one photon. Number of something is always total over the amount for one. The number of half-lives is equal to the total time divided by the time for one half-life. So it's T over T 1/2. Okay, that one's not on our data sheet, but it's a fairly easy one to come up with. This one is on our data sheet, and a lot of you have seen this one before as well in math class. N is equal to n sub 0 1/2 to the little n. N is the number of half-lives, little n is. Big N is the amount that remains, and n sub 0 is the amount that you start with. Now, n and n0 can be just about any units you want. Kilograms, grams, moles, just a number. It can be percent. On your worksheet that you had for homework, we used becquerel a few times. A becquerel is a decay per second. Okay, it indicates an amount. As long as it indicates an amount, and as long as you're consistent between n and n0, it doesn't really matter what units you use. All right. First homework question that you guys asked to go over was question number 6. It says the activity of carbon-14 is 100 becquerel. What's the original activity if 2,000 years have elapsed? You got to know the half-life of carbon-14 for this, but that was given to you in a couple of other questions. 5,730 years. We can find little n, that's the number of half-lives, by simply saying T over T 1/2. So it's going to be, what is it, 2,000 years divided by 5,730 years. We do the math on that. And that works out to be, I don't have the number actually on my key. What is that? 0.349, and there'd be no units for that, right? Because it's just a number of half-lives. Okay, good. Now the next step is to say n is equal to n sub 0 1/2 to the little n. Solving for n sub 0, so this time it's taking the half to the little n over by dividing, this entire term over by dividing. So what do you got here? It's 100 divided by 0.5 to the 0.349, and that should give us 127 becquerel. Those units, becquerel, maybe you see them on a diploma exam, maybe you don't. Odds are you probably won't. Maybe you see another set of units for radioactive decay that you've never seen before. That's okay. You come across one of these questions involving half-life, and it's units you don't recognize, it's going to represent activity or something like that. Bottom line is it's going to be n or n sub 0. So you don't need to really, truly know what the unit represents or know what the unit is, as long as you know that it represents amount, n or n sub 0. Hey, one more quick little thing before we move on to the next question. Whenever I write years, I always write it as a y. You may see it sometimes written as an A. Where do you think that comes from? Where's the A come from? It means the same thing. 2000A or 2000Y means the same thing. Lucas or Shanda? Okay. No, it's actually, well, in a roundabout way, yeah. What's the French word for year? Yeah. And where does that come from? It comes from Latin. Yeah. Yeah. So it's annum Latin. So same, guys, it means the exact same thing as a year, right? So if you see an A, don't panic about it. Okay, it's just a year. In the end, hey, if you were given both of these in A's, whatever, even if you didn't know what that was, you could still solve this problem, right? As long as you recognize it's a time. Okay. Number 7. 7 and 8 gave a number of people trouble, I think. These ratio things. Please remember this. And if you don't remember this, please write it down now. If you ever see the word ratio, if you ever see the word compare, then what you need to do is divide. If you see the word ratio, you see the word compare, you divide. How many times have we used that analogy of my age to your age for one thing or another? We've used it several times when we've been asked to compare two things or to find the ratio of two things. Okay, hey, what's the ratio of my age to your age? 2 to 1, right? Okay, you're 18, I'm 36-ish. Divide 36 by 18 gives me a ratio of 2 to 1. When we want to find a ratio or we want to compare, we divide. Here we want to find a ratio of current activity, okay, which is an amount, okay, n, to the original activity, which is n0. So let's divide n by n0. The problem is, it's a small problem, but a little bit of a problem. I don't know what n or n0 is. But this is kind of like the whole charge to mass ratio thing that you guys found here just before Christmas. Remember charge to mass ratio, cathode ray tube? If we know the charge and we know the mass, then let's just divide them. But we don't know the charge and we don't know the mass, usually at least. So we have to come up with an equation that's the same thing as charge over mass. And if you remember from the cathode ray tube, we derived that equation, V over BR. So we found charge to mass ratio not by dividing Q over M, but by doing this, which gives me the same thing as Q over M. Well, let's get an equation for n over n0 since we don't know what n or n0 is. It comes from this one. Let's take the n0 over by dividing. It becomes 1/2 to the little n. So really all we have to do, find a little n, that's going to be t over t 1/2. It's 11,460 years divided by 5,730 years. Gives me 2 half-lives. Plug it in here. We get a number that's, I believe it worked out to be 0.25, I think. Yeah. That means our ratio would be 0.25 to 1, or some of you may have said 1 to 4. Okay. If you got the two numbers that you're supposed to divide, great. It makes it easy. But if you don't, just come up with an equation that will give you the same thing as those two numbers divided. Right? How many people we got 0.25 to 1? How many people said 1 to 4? Okay. Same thing, obviously. 1 to 4 is a little bit neater, right? But no more correct, though. All right, number 8. We got a similar thing here. We want to compare the activity to its original activity. So once again, we're going to say n over n0. It doesn't say find a ratio, it just says compare. But it's the same thing. 1/2 to the little n. We're going to find n the same way. It's 17 days divided by 5 days. It's going to give me 3.4. And that gives me a number of 0.0947. So you could say 0.0947 to 1, or what I said was the activity is 9.47% of the original activity. Okay. As a ratio, we don't express it as a percent, but when we're asked to compare, a percent is fine. How many people got that one? For those of you who struggled a little bit with some of these questions, is it making a little bit more sense? All right. Thanks for your input there. Number 9. How many half-lives would it take for 10 grams of a radioactive sample to decay to 1.25 grams? How many people used logarithms for this? Okay, how many people use the divide by 2 method? Okay, you know what? I'm going to use the divide by 2 method, because if you tried using the logarithm method and you got the wrong answer or it didn't work, then you probably shouldn't try using the logarithm method. You probably should go back to this method. If you're good with logs, great. If not, then do this method, the divide by 2. So there's my little table. After 0 half-lives, I got 10 grams. After 1 half-life, I got 5 grams. 2 half-lives, I get 2.5. After 3 half-lives, I've got 1.25. So little n would be equal to 3 there. Just keep dividing by 2 until you get your final amount. 10, almost the same question, number 10. After 1 half-life, I got 5. No, wait, not 10. It should be 100, shouldn't it? 100%. After 1 half-life, I got 50. After 2 half-lives, I got 25. N would be 2. And finally, number 11, how many years would it take for 20 grams of carbon-14 to decay to 10 grams? Let's first get the number of half-lives for each of these. Okay. For the first one, you know, let's just make a big table over here. 0 half-lives, 20 grams. 1, 10 grams. 2, 5 grams. 3, 2.5 grams. 4, 1.25 grams. 5 half-lives, 0.625 grams. Okay, 10 grams would be 1 half-life. 2.5 grams would be 3 half-lives, 4 half-lives, and 5 half-lives. How are we going to find how many years that is now? Easy at this point, right? How many years is it? If we have the number of half-lives and we know the half-life from a few of the other questions, let's just multiply 1 by that, 3 by that, 4 by that, 5 by that, and we get our answers. Okay, any more questions on that page? Good? All right. There's one more little thing that I want to show you with radioactivity, and then we'll move on to a new topic, which is kind of related to radioactivity, but not radioactivity per se. I've told you guys that you will see a question on your diploma exam that involves a graph. You will. And it will be almost certainly a straight line graph. You know how to deal with a straight line graph, even if it's a graph that you've never seen before. Do the whole y equals mx plus b, get the equation from your graph, get the equation from your data sheet, and then figure out what the slope represents, figure out what the y-intercept represents, so on. You know how to deal with that. But if you see a graph that's curved like this one, this radioactive decay curve, you may not know how to deal with it. This curved line graph will almost certainly not be that one numeric response graphing question that I'm talking about. Okay, but you could still see this curved line graph where you're asked to interpret it as a separate question. Good news is it's easy. What's the graph represent here, first of all? Well, we've got mass of a radioactive substance versus time. So in other words, we've got n, the amount that we have. Maybe it's mass, maybe it's measured in percent, maybe it's just a number. Maybe it's measured in becquerel. It's n. It's the amount that remains versus time. And the shape of that graph always, every single time, will be this. If you've taken Math 30, you've probably seen this graph before. Right? It's an exponential decay graph, exponential decay curve. The good news is all we have to be able to find for this graph are two things. And both of those things are really easy to find. The first thing that we may need to find is an amount. How much remains after 5 years? How much remains after 2 years? How much remains after 12 years? If you want to find an amount, then all you're going to do is go up and over. How much remains after 5 years? Go up from 5, over, and it looks to be somewhere close to 20. How much remains after 2 years? Go up and over, looks to be about 50 grams. You want to find out how much remains after a certain amount of time. You want to find an amount, then go up and over. If, on the other hand, you want to find a time, how long does it take to go down to 25 grams? How long does it take to go down to 75 grams? What's the half-life? If you want to find a time, then you're going to go over and down. How long does it take to get down to 60 grams? Go over and down. How long does it take to get down to 40 grams? Go over and down. What's the half-life? What's the half-life? There's a good question. How much do you have left after one half-life? Started with 100. After one half-life, we've got 50. So go over to 50 and then go over and down. Looks to be about 2 years. That's all you got to do on these graphs. Up and over, or over and down. And you never have to worry about forgetting which you do. Okay, if you're looking for a time, then you gotta go over and down to intersect with time. You want to find a number? Up and over, intersect with time. Good? Okay, I'll leave you with question number 12 on your worksheet. Not going to work on that right now, but I'd ask you to work on that for homework tonight. It's probably going to take you about 60 seconds maybe to do that question. Okay, if you struggle with it, let me know. I think you'll be okay with it though.